Imagine building a digital brain so massive, so incredibly complex that if you tried to actually turn it on, there literally wasn't a single computer on planet Earth big enough to hold it.
Right, which is just a wild concept to start with.
It really is. I mean, you open up an app today, you type a question into ChatGPT, and a perfectly formed answer just appears on your screen, right?
Yeah, totally instant.
Exactly. There is this really powerful illusion of simplicity for you as the user. You probably assume there's just this sleek, glowing monolith of artificial intelligence sitting in a pristine server room somewhere, calmly doing the math and handing you the result.
It is a very comforting image, honestly. The idea of this isolated, super smart machine just silently pondering the mysteries of the universe.
Right, like a digital oracle or something.
Yeah, exactly.
But the reality of how that system actually works and how it was even built in the first place is less like a quiet monolith and more like trying to contain a raging digital hurricane.
Oh, absolutely. It's chaos behind the scenes.
It really is. And today, we are completely shattering that illusion of the quiet monolith. We are jumping into a brilliant piece published today, June 20th, 2026, in Tech Reader magazine.
Yes, by Aaron Rose.
Right. It's titled The Software War Rooms, How Distributed Systems Made ChatGPT Possible.
Which is such a remarkable piece of journalism, I have to say.
Yeah.
Because it deliberately shifts the focus away from the AI model itself.
Totally.
Like, it shines a massive spotlight on the sheer, brutal software engineering gauntlet that had to be run just to keep the model alive long enough to learn anything.
Yeah. And that's our mission for you today. We're going completely behind the curtain. We aren't going to focus on neural networks or prompt engineering or even how smart the AI is.
Right. No intelligence debates today.
Exactly. We are uncovering the colossal, invisible, and highly unstable machinery that allowed this model to exist at all. Because, everyone knows the AI, but almost nobody knows the gauntlet.
It's the invisible infrastructure.
Exactly. Okay, let's unpack this. To start, let's look at the earliest internal demos of the model that would eventually become ChatGPT. The engineers at OpenAI hit a wall that wasn't just a difficult math problem.
No, it was a physical impossibility.
Right, a physical impossibility.
And we really need to understand what physically impossible means in this context, because it sounds like exaggeration, but it's not.
It's literal.
Yeah. When you build an AI model, it consists of billions, sometimes trillions, of parameters.
Which are basically the mathematical weights that determine how it thinks, right?
Exactly. And to run or train that model, all of those parameters have to be loaded into the active memory, or the RAM, of a graphics processing unit, a GPU.
Okay.
The prototypes they were building in the lab were astonishingly smart, but they were monstrously huge. Like, a standard high-end GPU might have 80 gigabytes of memory.
Which is a lot for a normal computer.
Right, but this model required terabytes just to wake up. It was simply too large to fit on any single piece of hardware in existence. It was, as the author describes it, bigger than the physical world as it existed.
Man, that phrase just stopped me when I read it. Bigger than the physical world.
That's heavy.
It really is. So you have this revolutionary intelligence, but literally no physical container big enough to hold its brain. That sounds like trying to fit an entire multi-volume set of encyclopedias onto a single Post-it note.
That's a great way to put it.
You physically cannot squeeze the ink onto the paper.
Precisely. So if you can't build a bigger Post-it note, your only viable solution is distribution. You have to break the encyclopedia apart.
Okay, so you chop it up.
Right. But we're not talking about simple distributed computing here where you just send a basic isolated task to a second computer. They had to turn this model into a living swarm.
A swarm?
Yeah. The model itself had to be sliced into tiny fragments called shards. Each shard then lives on a different processor, on a different server, sometimes in a different rack entirely.
And it wasn't just the model being sliced up, right? The training data, like the massive libraries of text it was learning from, had to be sliced up and fed through this swarm, too.
Correct. The data has to flow through the network, touching every single shard of the model in the exact right order.
Which sounds incredibly complicated.
It is. And because these shards are constantly updating their mathematical weights based on what they learn, they have to constantly talk to each other.
Like, I just learned this. Update your math.
Exactly. Now I need your updated math to process my next piece of data. You're trying to make thousands of distinct, physically separate processors, all connected by miles of networking cables, act as one single coherent, unified machine.
Okay, but hold on, I'm stuck on something here. It's like trying to run a massive river through a canyon, but you have to perfectly slice the water so every drop hits the right rock at the exact right millisecond.
That is exactly what it's like.
Well, wait, the story notes they partnered with Microsoft Azure for
Yes,
this.
they did.
And Azure is already one of the biggest, most sophisticated cloud computing platforms on the planet. They have vast, mind-boggling amounts of compute power sitting in warehouses all over the world.
Oh, massive amounts.
So why couldn't OpenAI just, rent a massive warehouse full of Azure servers, load the shards onto them, and just hit run? Why is the sharding process so incredibly difficult if the power is there?
Well, because raw computing power is entirely different from orchestrated computing power.
Okay, how so?
Having 1,000 incredibly fast engines doesn't give you a functioning rocket ship unless they fire in perfect synchronized harmony to the millisecond.
Oh, I see.
Raw compute is just the material. To make it work for an AI of this scale, you need an orchestration layer. You need complex scheduling software that dictates exactly which GPU is doing what at any given microsecond.
So it's not just about the hardware, it's the management of it.
Right. And you need extreme fault tolerance, because in a cluster of thousands of computers, the hardware fails constantly.
Just from normal wear and tear.
Yeah. A cable gets bumped, a power supply dies, a memory chip fries. You need a software layer that fundamentally tricks those thousands of disparate GPUs into believing they are a single organism.
Ow!
And it has to be able to route around a dead GPU instantly without the whole system crashing.
Which brings us to what happened when they first tried to marry OpenAI's lab prototypes with Azure's massive raw compute.
Yeah, this part is wild. The very first attempt to run this distributed stack on Azure lasted exactly 15 minutes before the entire thing collapsed in on itself.
15 minutes.
Just 15.
They plug it in, flip the switch, and a quarter of an hour later, it's a smoking crater.
Basically, yeah.
And that spectacular failure forced a massive realization for both companies. I mean, this wasn't a hardware problem where you just buy more servers or plug in thicker cores.
Yeah, not at all.
It was an orchestration problem of unprecedented scale.
Yeah.
It forced a radical shift, not just in the technology, but in the actual human beings building it.
Yeah, that 15-minute crash was the catalyst for an intense physical and cultural merger. The realization hit both Microsoft and OpenAI immediately.
Like, they couldn't just slack each other to fix this.
Exactly. They could not solve this over routine video calls or by tossing code back and forth over email. They needed to embed together completely.
Engineers from OpenAI literally packed bags and flew out to Redmond, Washington. Azure engineers flew down to San Francisco.
Real physical war rooms were formed.
Yeah, whiteboards were completely covered in schematics, monitors were multiplying on desks, and the corporate boundary between Microsoft and OpenAI essentially dissolved in those rooms. People just stopped caring who signed their paychecks.
But, merging the physical spaces was the easy part. The real friction came from the cultural collision.
Oh, yeah, two totally different worlds.
Completely opposing engineering philosophies suddenly forced to share a keyboard. On one side, you have Microsoft's Azure team. Their entire existence is built around building infrastructure for the biggest banks, hospitals, and corporations in the world.
High stakes, reliable stuff.
Right. Their culture is rooted in enterprise-grade reliability, strict service-level agreements, and meticulous disaster recovery playbooks. They are the guardians of stability. They build things to never, ever go down.
And on the other side, you have the OpenAI engineers. Their culture is rooted in a cutting-edge research lab environment.
Very different vibe.
Oh, completely. They are used to moving incredibly fast, testing wild hypotheses, and breaking things daily. The author specifically notes they were the type of engineering team to completely rewrite entire foundational subsystems on a Tuesday afternoon just because someone had a brilliant new idea at lunch.
Which is how you get friction.
Yeah.
The first few weeks in these war rooms felt like a fundamental clash of operating systems.
I can't even imagine managing that room. You've got the disaster playbook, never let it break crew working shoulder to shoulder with the move fast, rewrite it on a Tuesday crew.
It's a lot of tension.
It sounds like trying to merge a team of strict aviation engineers building a commercial jet with a team of Silicon Valley startup sprinters who want to swap out the engines while the plane is already taxiing down the runway.
What's fascinating here is that this fusion was not a corporate team-building exercise. It was a mandatory requirement for the project's survival.
They had no choice.
None. The startup sprinters desperately needed the aviation engineers' rigid structure just to keep the cluster from catching fire. But the aviation engineers needed the sprinter's sheer reckless velocity and willingness to try insane mathematical approaches to achieve something that had never been done.
Right, because the problem of training a model that no single machine could contain demanded absolute total alignment.
Exactly.
So they had to forge completely new culture, and they had to do it immediately because this newly fused team was about to set up their first real scaling run.
Yeah. They decided not to jump to thousands of GPUs right away.
Just a few hundred to test the waters. But just as the human cultures had initially clashed, the underlying code of these two systems collided in the most spectacular, terrifying way imaginable.
Oh, it failed instantly.
Yeah.
But it wasn't a normal software failure where an app just quietly freezes or throws a neat little error message.
The logs from this failure are unbelievable. It's literally like reading a crime scene report from a science fiction movie.
It really is.
Processes are dying out of nowhere with zero explanation. Entire computer nodes are just dropping out of the cluster like they vanished into thin air.
The data pipeline's completely stalled.
Yeah. But the most alarming part was the distributed optimizer, the part of the software trying to manage the learning process. It diverged so wildly that the loss curve looked like a seismograph during a major earthquake.
Right, and let's define what that loss curve is, because it's vital.
Please do.
When an AI trains, the loss is basically a measurement of how wrong its answers are. You want that curve to smoothly, steadily go down over time as the AI gets smarter.
Okay, so a smooth downward slope.
Exactly. When that curve looks like an earthquake, spiking wildly up and down, it means the model isn't learning. It's experiencing mathematical chaos. The system was completely losing its grip on the physical laws of computing.
Yeah, because one of the servers literally reported a temperature reading of absolute 0.
Which is impossible.
Right. Physically impossible unless the server farm was somehow transported into deep space. And another node claimed that it had processed 9 quintillion tokens in a single second.
Which is just staggering.
And just for context for you listening, a token is roughly a piece of a word that the AI processes. Processing 9 quintillion of them in a second defies the physical limits of how fast electricity can move through silicon.
It's completely absurd.
The system wasn't just breaking, it was hallucinating its own demise.
We have to look at the mechanics of why this happened, though. The engineers were staring at monitoring dashboards where everything that could go wrong was going wrong simultaneously.
It wasn't just a typo then.
No, it wasn't a typo in the code. It was a perfect storm of mismatched assumptions. When you build software, you build it assuming the environment you are running it in will behave in a certain predictable way.
Like assuming gravity will work when you step out of bed.
Exactly. OpenAI's distributed training code was originally built in a highly controlled lab environment. It had hard-coded assumptions about network timings.
Oh, I see.
Yeah, it assumed that when shard A sent a message to shard B, it would arrive in a highly specific microscopic fraction of a millisecond. But Azure is a massive multi-tenant cloud infrastructure spanning acres of real estate.
Right, it's shared space.
Yes. Network traffic fluctuates. Sometimes a message takes a fraction of a millisecond longer to cross a warehouse.
So the OpenAI software says, I didn't get the message in exactly 0.1 milliseconds, so shard B must be dead, and it just panics.
Right.
But shard B isn't dead at all. The message was just a tiny bit delayed by the physical reality of the cloud.
That is exactly the mechanism. Meanwhile, Azure's cluster scheduler, the software assigning the jobs, assumed these AI tasks would behave in a certain predictable way. But OpenAI's workloads were wildly erratic, pulling massive amounts of power in sudden bursts.
Just totally out of sync.
And furthermore, the data loader, the system responsible for pulling the text libraries into the GPUs, was looking for file system semantics that don't exist in a cloud environment.
Wait, what does file system semantics mean in this case?
It means the OpenAI code was looking for a traditional hard drive. It was asking, go to the C drive, open this folder, and read this file.
Like on a normal laptop.
Exactly. But Azure's massive data lakes don't work like local hard drives. They use blob storage, which requires a completely different way of asking for data. The OpenAI code was frantically searching for a physical drawer in a filing cabinet that simply wasn't there.
Okay, here's where it gets really interesting to me. If a system is throwing out errors that defy the laws of physics, if it is telling you it is sitting at absolute 0 because a thermal sensor API completely broke down from network chaos, how do you even begin to patch that?
Well, you can't.
Right. You can't just slap a patch on something so completely untethered from reality.
The harsh reality of software engineering at this massive scale is that you don't patch it. When a system's core assumptions are that fundamentally mismatched, a patch is just putting a Band-Aid on a sinking ship.
Yeah.
You have to accept the hardest truth in the industry. You have to tear the entire thing down to the studs and rebuild it from scratch.
And that is exactly what this Fuse team of enterprise guardians and research sprinters did. They realized early on they couldn't patch their way out of this nightmare.
We had to start over.
They rolled up their sleeves and touched every single layer of the stack in what became known as the Great Rewrite.
It was a comprehensive, exhausting overhaul. They completely redesigned the orchestration layer to handle the specific, messy physical quirks of cloud networking.
Which must have taken forever.
Oh, absolutely.
Yeah.
They had to rebuild the data pipeline to handle data streaming at a scale that would have been laughed out of a room a year prior.
To visualize that data pipeline, it's like they were trying to route millions of high-speed bullet trains through a massive interconnected rail network.
Yes.
And ensuring that every single train arrives at the exact right station at the exact right microsecond without any of them ever colliding or having to hit the brakes.
And doing that requires completely new infrastructure. I mean, they even had to build their own internal tools just to see what they were doing.
Really?
Yeah, the old debugging tools literally couldn't handle the sheer volume of error logs the system was spitting out. The monitoring dashboards would melt under the load. They had to build faster checkpointing systems.
What's checkpointing?
Checkpointing is basically how the system saves its progress. If a run crashes after 3 days, you don't want to start over from minute 1, right?
Oh, of course, like saving a video game.
Exactly. You load the last checkpoint.
Yeah.
But their old checkpointing system was so slow that it was taking longer to save the model than it was to train it. From the massive cluster schedulers all the way down to the basic Python scripts, everything was rewritten.
That is nuts. And the staggering effort of that rewrite led them to a massive milestone. They scaled the system up to just over 1,000 GPUs.
A huge deal at the time.
The war room is buzzing. Engineers are highly caffeinated. They hit run. And for a few minutes, it is glorious.
It actually worked.
Right. The shards are actually talking to each other. The beta trains are hitting their stations perfectly. The loss curve, that seismograph, is going down smoothly. The AI is learning. Then
it freezes.
not a crash, not an error message, just a total absolute freeze.
Yeah, in distributed systems, this is known as a deadlock.
Yeah.
And it is the absolute worst-case scenario an engineer can face.
Worse than a crash.
Oh, much worse. When a system crashes, it's violent, but it leaves a trace. It throws an error code. It dumps a log. It leaves a breadcrumb trail for engineers to follow and investigate.
It gives you a crew.
Exactly. But a deadlock gives you absolutely nothing. Every single process in that 1,000 GPU cluster simply hung in place, waiting for a message from another process that was never going to arrive.
Wow.
The error logs were completely empty because technically the system didn't think it was broken. It was just waiting. It had entered a state of paralysis that no one had ever encountered before.
So it's basically a massive Mexican standoff. Thousands of GPUs all pointing at each other saying, you go first, no, you go first, until the end of time.
That is precisely the mechanism of a deadlock.
Yeah.
And diagnosing one at that scale is pure agony. It took the combined engineering teams 3 full days to figure out what went wrong.
3 days of just staring at screens.
3 days of manually tracing logs, instrumenting the code to print out exactly what it was doing at every microsecond, and arguing over theories.
You would think a failure that brings down 1,000 GPU cluster would be a massive architectural flaw, like some huge miscalculation in the physics of the data center.
No, it was a single line of code.
One line.
Just one line in the distributed optimizer. Under incredibly rare, highly specific timing conditions, this single line of code would trigger what's called a shared memory lock.
Wait, can you break down what a shared memory lock actually is for us?
Imagine 2 different shards of the AI model both realize they need to read the exact same page of a reference book at the exact same microsecond.
Okay.
To prevent them from trying to turn the page at the same time and tearing it, the system uses a lock. One shard grabs the book, locks the door, reads what it needs, unlocks the door, and hands it to the next shard.
That makes sense.
But because of a tiny timing error in that single line of code, shard A grabbed the lock, but shard B also thought it had the lock.
Oh, no.
Right? Shard A was waiting for B to finish, and B was waiting for A to finish. Neither would let go of the book.
And because the entire neural network is mathematically connected, that one tiny localized standoff rippled outward. Shard C is waiting on B, shard D is waiting on C, and within milliseconds, the entire 1,000-node cluster is paralyzed.
Exactly. 72 hours of agonizing around-the-clock detective work to find one single line of code buried in millions.
And how long did it actually take to rewrite that line of code once they finally found it?
10 minutes.
72 hours to find the needle in the haystack, 10 minutes to snap it in half. That is just incredible.
It is.
That single line of code was the turning point for the entire project. But the ultimate victory wasn't exactly what you would expect. There were no massive celebrations. The system didn't suddenly wake up and work flawlessly forever.
Right, because there is no magic bullet in distributed systems. Fixing that deadlock was crucial, but it really just cleared the fog so they could see the next bottleneck. Achieving actual stability was a grind. It was 1,000 tiny, unglamorous improvements.
It was a relentless iteration process. Let's dig into some of those fixes. How do you actually keep a cluster of that size stable once the big bugs are gone?
You build in resilience to physical reality. They wrote new communication protocols that reduced the amount of chatter between shards so the network cables wouldn't get clogged.
Okay, so better traffic control.
Yes. They built new strategies to load data asynchronously.
Meaning what, exactly?
Meaning the GPU didn't have to sit idle waiting for the next batch of text to arrive. The system would prefetch it and have it waiting in memory. And they built sophisticated heartbeat monitors.
Heartbeats, like for the computers.
Yeah, so if a computer node literally caught fire or randomly dropped dead, the orchestrator would instantly notice the heartbeat stop. It would seamlessly reroute that shard's workload to a backup node and keep the massive training run alive without human intervention. Piece by piece, the beast was tamed.
And you can actually track that stabilization in the runtimes. After the deadlock was resolved, the next run lasted an hour before failing. Then they tweaked the heartbeats and got a run to last 2 hours, then 12 hours, and then finally a full day without a crash. The loss curve finally started descending smoothly and predictably. The system was holding together.
And once 1,000 GPUs are stable, they push the envelope, they go to 2,000, then 5,000.
It's a massive jump.
Sure, and they hit new weird issues at that scale, like memory fragmentation, where the RAM gets chopped up into unusable tiny blocks, or network jitters. But the failures are contained now. The orchestrator is catching them. The system isn't hallucinating absolute zero anymore. It has matured into a stable organism.
Which leads directly to the final training run, the actual historical run that birthed the ChatGPT model we know today. And the author points out that this monumental moment in human history was, well, completely boring.
It was anticlimactic by design. The final training run went on for weeks. It checkpointed its progress cleanly. When hardware inevitably failed during those weeks, the software orchestrated a recovery without any drama. The war rooms, which had previously been chaotic zones of panic and whiteboard scribbling, were now totally quiet.
So what does this all mean? We are talking about arguably the biggest technological breakthrough in modern history. And the engineers who made it happen didn't pop champagne or cheer. They just sat in a room, exhausted, staring at boring green dashboards in total disbelief that it wasn't crashing. The magic of ChatGPT was actually born in the sheer monotony of a massively complex system finally doing exactly what it was told.
If we connect this to the bigger picture, it fundamentally changes how we should view artificial intelligence. The public narrative is always focused entirely on the AI model itself.
Right, the intelligence.
We think progress is just about feeding more data into bigger mathematical equations, but none of that intelligence exists without the invisible heroics of the software engineers who built the orchestration layer. The data pipelines that stream terabytes of text without choking. The cluster schedulers that keep a massive run alive when physical servers fail. The AI model is the shiny headline. But the distributed system that acts as its life support, the software that forces thousands of machines to act as one, that is the actual story.
And that is exactly why this deep dive is so important for you to hear. Because the next time you open up that app and you type in a prompt and you get an instant, flawless response, you'll know the truth.
It's not magic.
No, you are just talking to a smart brain floating gracefully in the ether. You are querying a highly volatile, massively distributed living organism of code, a digital swarm spanning thousands of physical processors that was violently forced into stability by a team of exhausted engineers who simply refused to let it collapse.
And that brings us to a critical realization to leave you with. The article notes that this story is far from over. These models are only getting larger.
Oh, they're growing fast.
So, if the true bottleneck of AI progress isn't the intelligence of the math itself, but rather our human ability to build the distributed software needed to contain it, what happens when these models grow so massive they can't even fit inside a single data center?
Oh, wow.
When training a single model requires the synchronized orchestration of the entire planet's computing power across continents and oceans, can our software actually hold that together, or will the swarm freeze again?
That is a massive question for you to mull over today. Thank you so much for joining us on this deep dive. Keep questioning the invisible machinery behind the magic, and we will catch you next time.